All
Thank you
right,
for that.
thank you. Good evening, Sharks, and thank you for your interest in our seminar. So the premise is that the future of logistics, infrastructure, and surveillance is autonomous. But as we'll show you today, the future is currently built on a vulnerable foundation. We are Group A, and we are presenting a zero trust architecture for securing unmanned aerial vehicle systems. To address the threats that we've identified, we have worked as a team utilizing our cybersecurity and systems engineering backgrounds to develop what we will present today. I'm Edward Hickey. I'm proud to stand today alongside our team lead, Isan Barmil, and our engineering partners. Together, we have analyzed the gaps in the current national airspace and architected a solution to one of the single greatest threats to the economic viability of autonomous systems. Let's begin by establishing the relevance to UTM, unmanned traffic management. What you see on this dashboard is not a single fleet of drones. This is a representation of the unmanned traffic management infrastructure, the digital air traffic control required to coordinate hundreds of independent operators simultaneously. The green flight paths are not just dots on the screen. They represent commercial fleets scaling to millions of flights. The market for software infrastructure alone is projected to reach $6.2 billion by 2034. The technology is ready and the business case is proven. But this ecosystem has a fatal flaw. The industry relies on perimeter security, which creates implicit trust. This red dashboard represents a token replay attack. Because legacy firewalls trust anyone with a valid login, the system cannot distinguish between a legitimate drone and a rogue actor. This is a business kill switch. To ensure safety, the immediate response is operational paralysis, grounding the entire fleet until identity is proven. This impact creates existential risk for three key stakeholders. First, the public. One spoofing incident destroys trust in drone corridors. Second, for regulators, if you cannot guarantee identity, you face regulatory revocation. You lose your license to operate. And finally, the business. You face loss of revenue and liability exposure. Worst of all, if you're grounded while your competitors fly, your market share flies away with them. We cannot build a billion-dollar industry on an architecture that creates this level of liability. To solve this problem, we have to look beyond the software code. We analyze the system architecture itself, identify gaps, and derive high-level requirements for a solution. To solve the system architecture defined in the FAA Concept of Operations version 2.0, as shown here, the federated system. The FAA is on the right, but operators are managed by the USS network on the left, a cloud of private competing vendors. This architecture demands high volume, real time data exchange between disparate entities. That connectivity is the operational requirement. However, we identified a critical gap: static trust. In the current model, once a peer USS is authenticated, the firewall trusts it indefinitely. This enables lateral movement, as shown by the red. If an attacker compromises a peer USS, they ride that trusted link to inject fake data into the target USS. The firewall sees a valid login and lets the attack through. The architecture itself is the vulnerability. We map these gaps to derive three new high-level requirements. First, for connectivity versus trust. We must share data, but we cannot trust the link, which led to a requirement of moving from network security to transaction security. Second, for dynamics. Drones enter and exit instantly, so static logins fail to detect mid-flight hijacks, which led to a requirement of continuous verification on every heartbeat. And finally, for scale. Human monitoring cannot handle millions of flights. The requirement is automated policy enforcement. These derived requirements define our solution, zero trust architecture. I will now turn it over to my partners, Fatima and Mohammed, for further discussion of the identified threats and derived requirements that informed our solution.
Thank you, Edward. My name is Fatma Majid, and I will begin by examining Level 1 system architecture and identify the exact attack surfaces where use space is most susceptible to compromise. Next slide, please. This diagram shows the full operational pathway of a UMT mission. We start at the appropriate client where authentication tokens originate. If a token is stolen or replayed, every downstream system treats the attacker as the legitimate aircraft. At the identity provider, compromised credentials allow an adversary to evaluate privileges or impersonate an operator. Inside the Zero Trust Control Panel, the two most critical components are P1, Policy Enforcement Point, the checkpoint for all missions and delimited traffic. If P1 is bypassed or overloaded, the system loses authoritative visibility. And P2, Policy Decision Point, evaluates identify context, and safety constraint. A single incorrect decision can authorize a malicious mission or suppress an alert. Behind them are D1 policy store and D2 decision log. Tampering here lets attackers modify rules or erase evidence. Finally, P3 UMT services processes validated missions and telemetry. If falsified data reaches this layer, the system responds to the attacker instead of the aircraft. Together, this forms the full threat surface, and Zero Trust is designed to protect each boundary through continuous verification and strict policy enforcement. Now that we have seen the structural weaknesses, we can map how attackers exploit them on DFT. For spoofing, a stolen token is replayed, and without continuous verification, the PDP may authorize an attacker. For tampering, injected telemetry can mislead P3 into acting on false aircraft states. For reputation, weak or unsigned logs at P2 and D2 let attackers deny malicious activity. For information disclosure, weak IDP or policy store responses exposes sensitive roles and mission data. Denial of services means flooding P1 blocks real telemetry and leaving use space blind. Each stride thread maps to a specific architectural component and it is addressed by zero trust control. I'll now hand it over to Muhammad who will walk through our mitigations and formal requirements.
Thank you, Fatima. Hello, everyone. My name is Mohammed, and in this section, I'll highlight the key privacy risks in today's use space and how they shape the zero trust protection we design. Privacy is just as important as security. Operators, regulators, and customers all need the confidence that their data isn't being exposed or misused. So we built a fraud protection to address the most critical risks. First, we protect operators' identity. Remote ID can be tracked over time, so we rotate identifier to prevent long-term profiling of aircraft or pilots. Second, we protect mission data. Flight path reveals sensitive location, so all mission messages and telemetry are encrypted end-to-end, ensuring only authorized parties can access them. Third, we protect access. Mission logs often contain sensitive data, so we enforce a strict role-based permission and store only what is required for safety and compliance. And finally, we protect data integrity. All post-flight records are stored in a tamper-evident format, giving regulators and investigators confidence that the data is authentic. These controls are very simple, scalable, and integrable directly into how USpace already operates. Now, everything we've shown you so far, every threat, every failure, every architectural gap, all comes together here. This is where we translated our analysis into a formal enforceable system requirements. UTM cannot be secured with vague policies or best effort controls. It needs a measurable guarantee that operators, regulators, and service providers can depend on. So we defined a clear service level objective backed by zero trust control. For availability, the gateway must make, allow, or deny decisions fast enough to support real-time telemetry. If the system is too slow, safety breaks. For integrity, every mission request and telemetry messages must be validated on every interaction, not just once I logged in. For confidentiality, all mission data must be encrypted and accessed tightly controlled. Only the people who need to see it get to see it. And for auditability, every decision must be logged with structured context and explicit reasoning, giving regulators a verifiable records of system behavior. So now that we've defined what our solution must guarantee, the next step is to show you how we actually deliver on those guarantees. A system as dynamic and as fast-moving as USpace cannot be protected with band-aid fixes or bigger firewalls. It needs a model where every request and every aircraft prove its legitimacy every single time. Presenting zero trust, the solution we designed to meet these requirements. What we've built is a zero trust architecture tailored specifically for UTM, and the idea is simple. No one and nothing is trusted automatically. Every mission request, every telemetry update, every operator action must continually prove its legitimacy. At the core of the system are three components: the policy decision point, the policy information point, and policy enforcement points. The policy enforcement point is the gatekeeper. It inspects every request before it gets anywhere near critical UTM services. The policy decision point, it's the brain of this solution we have. It's evaluate identity, mission context, device posture, geofence status, and remote ID. The policy information point pushes out updated rules and handles the rapid verification of compromised credentials so they become useless almost immediately. Supporting these are strong identity management, short-lived tokens, encryption end-to-end, and micro-segmented services. The result is a UTM environment where trust is not assumed, it's continuously earned. And to show you exactly why this matters for UTM, I'll hand it over to my teammate Karthik for further.
Thank you, Mohammed. My name is Karthik, and I will walk you through how zero trust architecture strengthens security in UTM systems. Traditional perimeter security relies on implicit trust, which leaves UTM systems exposed to replay attacks, spoofing, and identity misuse. Zero Trust removes that weakness by requiring continuous authorization through a policy enforcement point and policy decision point workflow. Every request must prove legitimacy. Tokens, identity claims, mission context, and device posture are all verified on every transaction, ensuring users stay within approved parameters. Zero Trust also uses short-lived tokens and rapid revocation, so even if a credential is stolen, it becomes useless within minutes. Overall, Zero Trust gives UTM systems a dynamic, verifiable security foundation needed for safe and reliable operations. Now that we understand the technical importance of Zero Trust, I will highlight the operational and entrepreneurial value it creates. First, the architecture prevents unauthorized flights and airspace violations. This protects operators from financial penalties and interruptions in service. Second, the system supports real-time conformance monitoring and rapid threat containment. Violations are detected instantly and unsafe actions can be stopped on the spot. Third, Zero Trust preserves safety, public trust, and regulatory compliance through measurable service level objectives. Operators can demonstrate compliance and regulators gain clear visibility into decision making. The key idea is that Zero Trust does more than improve security. It supports business growth, reduces risk, and enables advanced operations in a sustainable way. Now I want to shift the focus to the people who stand to benefit the most from bringing Zero Trust into UTM. The first group is the operators. These are the companies that rely on drones for delivery, inspection, emergency response, and countless mission types. What they care about most is keeping their operations running without unexpected shutdowns or compliance problems. Zero Trust gives them a security foundation that prevents disruptions and keeps their approval to fly intact. In short, it protects both their mission and their business. Regulators benefit from clear, traceable decision making. Every action can be justified, which increases confidence when approving advanced operations. Service providers benefit because Zero Trust allows safe scaling. With strong policy enforcement and continuous validation, they can support more customers and introduce new services without increasing risk. Finally, the public benefits. Communities want safe skies, and critical infrastructure operators want assurance that nearby drones are legitimate. A stronger security layer increases trust and reduces opportunities for misuse. Overall, adoption makes sense because it strengthens security, increases confidence, lowers risk, and enables the level of growth that drone industry is aiming for. Now that you've seen the motivation behind our approach and the value it delivers, it's time to see what it looks like in action. Yazan and Pablo will take it over from here and walk you through the implementation of our Zero Trust system and the demonstration of its capabilities.
Thank you, Karthik. Hi, I'm Yazan Barmil, and in this section, Pablo and I will show how our Zero Trust architecture actually behaves in practice. First, we'll compare a simple pseudocode view of a legacy perimeter model against our ZTA, PEP, and PDP gateway. Then, we'll walk through screenshots from our prototype running 2 real-world UTM attack scenarios and highlight what those results mean for operators, regulators, and the public. Now, I'll pass it to my colleague Pablo to explain the legacy security system pseudocode diagram.
Thank you, Yaz. This is how a legacy perimeter-based system behaves under a token replay attack. In the first log line, we look at the check field. It only validates JWT signature expiry and revocation check false. On the left, we have the client, the drone operator sending an HTTPS request with a JWT, either for a flight plan or telemetry. The request hits the firewall in the middle. Its job is very simple. If the IP and port look okay, let it through. Otherwise, drop it. Once you're past the firewall, the legacy UTM app basically asks one question. Is the JWT signature valid and not expired? If yes, it runs the mission or stores the telemetry. If not, it returns a 401. What's missing here is the key. There's no per request revocation check, no device binding, no airspace class policy, and no real-time geofence enforcement. That's why in this baseline, all of our attacks can still succeed as long as they carry a valid-looking token from inside the network. So that's the old world. Once you're in, you're trusted. Now my colleague Yaz will show how our GTA gateway changes this logic.
Here's the same story in our zero trust design. First, in the client and IDP lanes, the operator requests a token. The IDP issues a short-lived JWT with a unique ID, the device ID, and specific scopes like mission write and mission read. Every call to UTM now goes through a dedicated PEP gateway, not straight to the app. The PEP checks TLS, validates the JWT signature, issuer, audience, and expiry, confirms the required scope, asks the IDP whether this GTI has been revoked, and makes sure the token's device ID matches the X device ID header. If any of those fail, the request is blocked right there. If the PEP is happy, it asks the PDB. The PDB builds context, operator, airspace, RID integrity, geofence status, and evaluates policies like, is the RID signature valid? Is this operator allowed in this airspace? Is the telemetry inside the geofence? The PDB returns an allow or deny plus a detailed log of action, allow, reason, and context. Allowed requests reach the UTM services, denied ones never touch the core. So instead of inside equals trusted, now we have continuous verification on every request. We implemented that pseudocode as a working prototype. This is our demo UI. On the left, we have multiple attack scenarios. However, for the sake of time, we're going to demonstrate two common ones today. On the right, we show what a legacy perimeter gateway would log and how our zero trust gateway actually responds. We'll walk through two examples to show how this design protects operators, regulators, and the public.
So this is how a perimeter-based system behaves under a token replay attack. So in the first log line, look at the checks field. It only validates JWT signature, expired, and verification check false. As long as the JWT is mathematically valid and not expired, the gateway trusts it. In the second line, we replay the same token after it's been revoked. The log still shows status equals 200 on plan submit, and the flags revocation check false, device binding equals false, and scopes checked equal false. From the legacy gateway point of view, this replay looks exactly like the first legitimate call, which is why token replay is such a big gap in the perimeter model.
Now, here's the same scenario in our zero trust gateway. First, a legitimate operator submits a flight plan. The PDB log for plan submit is green. Allow is true, reason is authorized, and the gateway returns 200 OK. Then the token is revoked. When we reuse that same token, the summary shows that the replay now gets 401 unauthorized, and the red PDB entry says allow is false, reason is revoked token with the JTI in the context. So unlike the legacy system, our gateway does a per request revocation check and gives us real-time blocking plus a clear forensic trail of why the replay was denied.
For the geofence breach scenario, the legacy picture is pretty stark. On the legacy side, the result box literally says no enforcement. Telemetry is just logged. It is not checked against any geofence, and there's no real-time alert. In the log below, the gateway only validates the JWT signature and expiry. There's no telemetry.conformance policy at all. Out-of-bounds data is stored exactly like normal data, so the only way anyone would notice a breach is by manually reviewing the logs after the fact.
On the zero trust side, we treat telemetry as something that must be continuously evaluated, not just stored. When the drone is inside the geofence, you see, okay, telemetry is 200 and a green PDB decision, telemetry.conformance allow is true, reason is within bounds, tied to aircraft ID UAV001. Even the okay case is an explicit decision. When the drone leaves the geofence, the behavior changes. The API shows breach telemetry is 202. And the PDB log turns red. Allow is false with reason, geofence breach detected, again linked to the same aircraft ID. So instead of silently collecting bad telemetry, our ZTA gateway actively classifies every message as compliant or non-compliant and generates a clear, machine-readable alert whenever a geofence breach occurs. With the legacy model, the answer to did someone see the violation in time is probably no. With our zero trust design, it's yes, and we can prove it from the logs. So that's how our zero trust gateway actually behaves under real UTM attacks. blocking misuse in real time, and giving regulators a clean audit trail. Now I'll hand it over to my colleague Fatima Majid, who will walk you through the key risks we identified, how we validated this prototype, and what results mean for deploying it in the real world.
Thank you, Yas. This section walks through the risk we identified, the experiments we ran, and the results that validate our zero trust approach. Here we highlight the key risk if these use spaces of vulnerabilities aren't addressed. A compromised UAS operator can have their identity used to submit false U plans, which flow through the USSP and CYSE without continuous verification. This leads to three major impacts: airspace safety risk, regulatory violations, and service disruption with loss of trust across the entire ecosystem. These consequences affect operators, service providers, regulators, and the public, and they show why zero trust is essential to ensure every request is continuously verified before it enters the airspace system. To validate a zero trust gateway, we ran three realistic UMT use cases. Two are mentioned over here due to time limit. First, in the first mission authorizing test, we replayed a stolen operator token. The legacy system accepted it while the zero trust gateway blocked it through recursion checks and device binding. Second, we tested telemetry integrity by injecting false attitude and location data. The legacy system logged it as valid, but the ZTA flagged it immediately through possibility checks. Across all experiments, the pattern was clear. Every attack bypassed the legacy model, and every attack was blocked or flagged by zero trust with full audit trails. Performance remained low latency, 35 to 50 milliseconds for policy validation, under 20 milliseconds for telemetry checks, and token recursion under 1 minute, showing ZTA can secure use space without slowing operations. Beyond stopping attacks, we also measured the quantitative and qualitative benefits for integrating zero trust into use space. Qualitatively, ZTA fully mitigated all tested attacks: token replay, telemetry manipulation, and restricted airspace misuse. Policy checks added under 50 milliseconds, telemetry checks under 20 milliseconds, and token evacuation completed in under a minute with zero false accepts. By filtering malicious traffic early, ZTA also reduces operator workload. Qualitatively, continuous verification improves airspace safety, temper evident logs, strengthen regulatory compliance, and operators gain confidence that identifies mission data cannot be misused. The system also becomes more resilient to credential theft and scales cleanly across multiple USSPs. Together, these benefits show that zero trust is not just a security enhancement, it is a practical enabler for safer, scalable use space operations. So that's how our Zero Trust Gateway performs under real UMT attack conditions, preventing misuse in real time and generating a complete regulatory audit trail. With our validation results and risks now laid out, I'll hand it over to Hui to bring everything together with the final conclusions and the broader implication for deploying the architecture in operational use space.
Thank you, Fatima. Hi, I'm Hui, and I will be covering the key takeaways, lesson learned, and our future plans to improve our product. To conclude, there are three main things we want you to remember. First, use space and UTM are too dynamic to rely on traditional perimeter. Once a token or device is inside, legacy systems have almost no visibility or control, which is why all our attack scenarios were effective. Second, those same attacks fail when we enforce zero trust at the gateway. Our PEP, PDP check all these important attributes on every request, not just a login. Third, the evidence isn't abstract. We show concrete HTTP outcomes and PDP decision logs that explain exactly why each malicious request is blocked or raises an alert. From a system engineering perspective, we learned three important lessons. First, continuous verification clearly outperforms one-time authentication. Second, attribute-based policies fit use space culture and requirements. And finally, decision logging is not a nice-to-have. These structured PDP logs we generated become a forensic record that are crucial after an incident. Looking ahead, there are several concrete steps. We plan to integrate this prototype with a fuller UTM stack and align the policy module more tightly with emerging use space standards and remote ID specifications. We also want to expand the policy set to cover performance and multi-tenant operations, then quantify the impact, measuring added latency, availability under load, and how many attack classes we can formally mitigate. That roadmap moves from a proof of concept gateway towards something that we could realistically sit in front of an operational UTM deployment. To make our final solution stronger, we invite investor-style feedback on two questions. One, which risks matter the most for operational adoption? latency, compliance, or inter-USSP complexity? And 2, which validation scenario would give you the greatest confidence in real-world deployability? In summary, we demonstrate why UTM needs zero trust. We show a working prototype enforcing continuous verification, and we outline our next validation steps toward a fully dependable system-level solution. We are ready to incorporate all your feedback and answer any questions that you may have. Thank you so much for the opportunity. Thank you for your time and attention.